Good afternoon to you, buon après-midi a vous, buon pomeriggio a tutti voi, guten Tag. Buenas tardes a ustedes. Welcome to Paris and to the International School of Astrophysics Daniel Chalonge-deVega for this seventh session of this year, and in particular the Nobel session in the Nobel program of this year of Nobel lectures in physics. And it's a great pleasure and a great honor to welcome here today Professor Dr. John Cromwell-Mather from NASA, Astrophysics and Cosmology Division, Nobel Prize in Physics for his achievement with the cosmic background explorer, the famous now COBE satellite, which started a new era, a modern era in precision cosmology. John Mather is also awarded a Nobel Prize in 2006, which he shared with George Smoot for the discoveries of both with COBE of the great precision in the spectrum of the microwave cosmic radiation and the discoveries of the anisotropies of this radiation. And we are proud too that John, for his many contribution, outstanding contribution to this school, is awarded with the Chalonge medal, one of the school medals, and in 2010. And is an expert in, very briefly, because I cannot take more time, it could be a very, very long description of his achievement, but just briefly, he's an expert in cosmology, infrared spectrophotometry, besides COBE, have served as advisory and working in working groups and experts groups in NASA, National Science Foundation, and for different instruments, particular for ALMA, and in Center of Astrophysics and Research in Antarctic. But also, just briefly, he got his PhD.
For that one, the power was set on 100 for
got his PhD in 74 from the University of California at Berkeley, then after enters as postdoc, in NASA, and performed his outstanding career till today. More. And I just before to give the floor to Sean, I want to say that today he will present the state of the James Webb Space Telescope, for which he is a senior project scientist from many years now, and also in this rich title he provided us, getting the James Webb Space Telescope ready, what it can do, new observational techniques for adaptive optics using orbiting laser guided stars. Would it be great to have nearly perfect imaging at the visible wavelengths with LT So I kindly ask all participants, please, to switch off their microphones and to switch off their videos to allow Professor Sean Mather, to allow Sean to start with his lectures. So please, you have the floor. Please, Sean.
Thank you, Norma. It's a pleasure to talk with you. And it's remarkable that we can now do this electronically. So despite all of the troubles with the pandemic these days, here we are able to work together scientifically and discuss our plans for the great future that is coming. So right here in this first picture, I am showing you the James Webb Telescope. This great golden hexagon in the center is the primary mirror. It is 6.5 meters in diameter, and it is being protected from the heat of the sun by a sunshade, which you see in 5 gray layers there, which is as large as a tennis court. Norma mentioned many of the awards that I have received, but I think it's obvious that when a project is as large as we do at NASA, that it's always a team project. 1,500 people worked on the Kobe satellite. Many, many thousands are working on the James Webb Space Telescope. And the Webb Telescope is available for use by all astronomers around the world. And we anticipate that basically everyone has access. So now I want to show you a little bit more about why I think this is so important, ducking back a little bit into history and what made the universe adopt its current structure. So sort of basic thoughts. How did the universe start? We know that it started out very smooth and very hot, that it was unstable because gravitation is able to release potential energy and turn it into kinetic energy. We know the universe is very large. We cannot prove that it is infinite, but it seems likely. At least to some of us, that the actual dimension is infinite. It's very old, which means that even very unusual events, such as the occurrence of life here on Earth, have had a chance to occur. We have learned about information storage and evolution, which I like to remind people is not directed, but is actually a matter of chance. We are the lucky ones. If we had had somewhat different luck, we would not be here, and perhaps the Neanderthals' descendants would be here having this conversation instead. We've learned about engineering. We've learned about how to design things that are stable. And we've learned that our human body is kept as it is by what biologists call homeostasis, which means basically feedback loops that maintain our identity by replacing dead cells with new ones that have the same function. So it's a remarkable story how we got here, and I think it's part of the reason that I've been excited about astronomy, because we are very interested in working out the physical story of how we got here also. So, of course, everyone knows that there are 4 main forces in physics: the strong, weak, electromagnetic, and gravity. Which are presumably all quantum mechanical. They tell us the shapes of the small pieces that can be reacting to each other to make large pieces. We know that gravity pulls things together and produces what astronomers call negative specific heat, which means that a gravitational system can heat itself up by converting potential energy into kinetic energy. We know about equilibrium thermodynamics, which means that if we have local order, as we have here in these, for instance, the living things here, we are accomplishing that by producing more entropy elsewhere. We are also aware that nature has a way to increase entropy by spontaneously produced heat engines. So a living thing is a heat engine that increases entropy of the universe while maintaining its own structure. So really remarkable story that is now more and more appreciated. But of course, astronomers want to work on how did it happen? How did the conditions occur for this to be possible? So over a century ago, we learned about the gravitational collapse. As James Jean told us when a gas cloud will collapse, when the gas pressure is greater than when the gravitational force is bigger than the gas pressure. So now we see this proven in images everywhere. We can calculate these things and show that this was the key insight that told us why the universe is unstable and will produce everything that we see from the original Big Bang material. So in 1929, we had the first evidence from Edwin Hubble that the universe is expanding. I like to show this chart because it was the first graph that showed the trend of the distance of galaxies versus the velocity of recession. So in his graph here, the slope tells us the age of the universe is about 2 billion years. As you know, there was a mistake in his distance scale, and we now know the correct age is about 14 billion. So this is the first time that we actually recognized as a community that the universe even has an age. So to summarize the whole story, I'd like to talk about it this way. There is no center, no edge that we can see. The infinite universe is expanding into itself. And something that many people in the public and even in sciences do not appreciate is there is no first moment in the expanding universe story that we tell. There is not actually an instant of creation. The way that the Big Bang is interpreted by public is a firecracker, a little explosion at a place and a time. We actually have in mind the infinite expansion of the infinite universe, which is not at a place and a time, it is everywhere. So our world community has been completely confused about the nature of the Big Bang. And so it's not too surprising that Sir Fred Hoyle didn't like it. Nevertheless, as far as we can tell, it's true.
John, we see no curve on the screen.
Please, please, I will tell. There is no graph now from your sharing in the screen. So the Hubble diagram did not appear and remained.
Oh, well,
frozen.
try again here.
Yes, perhaps you switched something in your.
Something changed, I suppose.
Yes. Now we don't we see you, but so you can
Okay, we have to try sharing the screen again, I think.
Yes, yes. You have the sharing of the screen, so you can do at your will.
Yes, so sharing screen failed, but we'll start again.
Because
Thank you for letting me know. Does that work? Is that better?
And no, that's a start. That's the message is shown. MATHER started to share the screen, which is the same message appeared from the Hubble diagram. So if you want to start from the beginning, I mean the slides, perhaps is something in this particular graph which are blocking something, because it's not only myself, all other participants also, but
oh, I'm sorry, I don't know what to do, but we will try changing something.
So you can perhaps start again with showing the slides, because it's not from our system.
Okay, we will try again.
No problem. We have time.
Okay, what do we see now?
Same message.
Huh.
while it was perfect, I mean, till this,
Until this moment.
yes, until this moment.
I think
It was the graph from the graph of the diagram of Hubble who now it's okay. Now it's okay.
okay, it sounds like internet trouble.
Yes.
So okay, so
no problem. No problem. It's you know, it's
okay. So thank you. So we'll continue. Anyway, this was Hubble's chart showing the expanding universe. And then do you see now my red chart with the early universe?
yes, yes.
Okay, so it's working again. So I was describing why the Big Bang picture is not the correct picture that people have. That people imagine that a Big Bang means a firecracker, like a small explosion, but it's actually the infinite universe expanding into itself. So, but I think that's more than I really wanted to say about that today, because I really want to tell you more about the telescope. So the Hubble Space Telescope is 30 years old now. It was launched in April of 1990, and it's about to be 31 years old, and we are very happy with it. It is still working very well, even though it is very old, because of course astronauts have been to visit it 5 times to repair it and improve it. Now here is the Webb telescope. As you know, it is a NASA project with international collaboration from both the European and Canadian space agencies. Our major contractor is Northrop Grumman, is a very large aerospace corporation. We have 4 instruments on board: a near-infrared camera, a near-infrared spectrograph, which was produced in Europe under supervision of ESA by a subsidiary of the Airbus Corporation. We have the mid-infrared instrument, which is produced by collaboration between the Jet Propulsion Lab in California and a consortium of 14 European institutions led by Gillian Wright at the UK Advanced Technology Center. And the 4th instrument is a combined fine guidance sensor and near-infrared imaging slitless spectrograph, which comes to us from Canada. Like the Webb telescope, it will be operated, like the Hubble Space Telescope, it will be operated from Baltimore by the Space Telescope Science Institute. The telescope has an aperture of 6.5 meters, is cooled to a very low temperature, approximately 40 Kelvin, so that it does not radiate very much infrared. And it is going to be launched on a European supplied Ariane 5 rocket in October, according to our plan. We are carrying fuel for at least 10 years of scientific operations. We have many different scientific themes that will certainly be explored by observers with this great telescope. Just to give a little bit of history, in 1995, there was a committee chaired by Alan Dressler that they wrote a beautiful report called HST and Beyond, the Hubble Space Telescope and Beyond. They told us to please build a new telescope that is good for infrared astronomy, and please also invest in the technology for searching for exoplanets like Earth around other stars like the sun. So there's Dan Golden. He was the head of NASA at the time. He spoke to the Astronomical Society and promised to go for a much larger telescope. He got a standing ovation, and so we knew that this was going to be very popular, even though it was going to be very difficult. So then we've been reviewed by the decadal surveys that we do in the United States. And so 2 surveys endorsed it. Now we're currently waiting for the launch date, which is planned by October 31st. So the main scientific themes are summarized here. The Big Bang, the first light and the reionization of the universe, the first objects to grow from the primordial material. We want to see how the galaxies grow from apparently from small parts merging together. We'd like to see stars being born, and stars being born with planetary systems around them. And finally, we would, of course, like to see the planets themselves. So here is an illustration of a coronagraphic observation, perhaps similar to what we will do with the Webb telescope. We have a very large group of people. This is our International Science Working Group. Includes people at NASA, people in Europe, and people in Canada. So I'm sure many of you that are observers and theorists will recognize these people. We have been working with most of them for most of this time. The official team was chosen in 2002, so almost 20 years ago. Here's the telescope design. We're showing you a large concave mirror, almost a parabolic ellipsoidal mirror, a hyperbolic secondary, and an elliptical tertiary mirror, which is all used to make a wide field of view, very accurate surface. The telescope primary mirror is made of 18 beryllium mirrors, hexagons, very, very thin, very, very lightweight, and they have been polished to have the correct shape when they are cold, down at 40 Kelvin. This was a huge engineering challenge, and it was successful. We have on board the 4 instruments that I mentioned. You can see here that they cover the entire wavelength range from 0.6 microns to 28.8 microns, which is capable of going from overlap with the Hubble cameras all the way out to wavelengths that certainly cannot be seen with a warm telescope. So the typical fields of view are of 2 arc minutes or so, which is very comparable to the cameras on the Hubble telescope. 3 of the 4 instruments include coronagraphic capabilities to look for those exoplanets, and also to look for these feeding zones of active galactic nuclei, the black holes that are growing with time. One very special feature is the near-infrared spectrograph, which is capable of observing 100 galaxies at one time. Spectroscopy has turned out to be very important. Approximately 70% of the selected observing time is devoted to spectroscopy. The telescope is incredibly sensitive. If you were a square centimeter of black body at the distance of the moon away from the telescope, we would be able to observe you through time exposures. We have more of a problem looking at very bright objects, but we have learned how to do it by reading out the detectors very rapidly. So all of the objects in the solar system from Mars on outwards can be observed. We can also do transit spectroscopy of stars looking for planets going in front of them. So a couple of graphs showing the relative sensitivity compared with other equipment. You see that even at 1 micron, the Hubble is still very powerful, but the Webb telescope is more powerful. And they're all far better than ground-based telescopes. Much more powerful because of being cold and being very, very, very large. So if you have a thing to look at out there, we have an exposure time calculator that you can use to say, well, how long an exposure do you need to see your favorite target? So just to summarize what is planned for the program, we have guaranteed time observers. These are about 4,000 hours of observing time dedicated to the teams that built the equipment or who were chosen as interdisciplinary scientists in 2002. We had a competition to choose early release science. So these programs were selected. 13 out of about 100 proposals were chosen. And all of those data will be made public immediately as soon as the observations are taken. and they cover a very wide range. I will show you some examples. And we had a competition for guest observers, general observers, and allocated 6,000 hours of time for them. So what did we get? We had almost 1,200 proposals for the general observers, and they cover every area that we were expecting, from the solar system to exoplanets to galaxies and cosmology, and even to black holes, the supermassive black holes. So everyone that could apply, well, anyway, there were enormous numbers of investigators, over 4,000 unique investigators in various roles, 44 countries involved. So we had the selection, and you can now look up the selection of who's doing what on the Space Telescope Science Institute website. So if you want to be an observer, there are YouTube channels you can find. Many seminars are available on our website, so you can learn how to use the equipment, how to use the data that are coming in, how to write proposals for the next time. So what are we going to look at? We certainly are going to look at the very first galaxies. The objective of seeing the very first galaxies was one of the most important ones. It was the one that said, build this telescope as large as you can, make it cold so you can see the redshifted distant universe. So we expect to see maybe 10 or 100 times as many galaxies as the Hubble could see, because the sensitivity is so much greater, and it can see farther back in time to see when the galaxies were young and still very small. So that's one thing we certainly know we're going to do. So we'll be looking at understanding the formation of those first galaxies. We know there were two major different cooling processes that enable gas clouds to collapse. One based on molecular hydrogen that can start working very early at a redshift of 25 or 30, and one that's more recent, which works at higher temperatures using atomic transitions. So this is the story we need to work out. When did the first stars form? Perhaps a redshift of 30. Then what happened next? We imagine and calculate that the very first stars were much, much more massive than the current generation of stars, because it was so hard for the gravitation to pull them together that the mass had to be much larger, perhaps a factor of 100 larger than current generations of stars. We've designed various observing programs to study the deep fields. This is a program devised by the guaranteed time observers. And you can see we're covering deep fields with all of the instruments that we have. So the work that's already been done on deep fields, where we know what's there already, will be extended dramatically with the Webb telescope observations. So here's an example or a demonstration that we'll be pointing our multi-object spectrometer at galaxy fields as well. We're showing here a typical image of the sky laid down on the array of microshutters. The way this instrument functions is to have about 250,000 small shutters that can be opened by command to allow the light from a selected galaxy to go into the spectrometer. So it's a very powerful and flexible instrument, and we expect it to give us wonderful surprises. So we will certainly be looking inside the gas clouds where stars are being born today. This is a picture showing the comparison of the visible view and the infrared view as seen with Hubble. So it's pointing out that the optical depth of the dust clouds is much greater at short wavelengths than at long wavelengths. The clouds become much more transparent as you go to longer wavelengths. So as we observe this with a Webb telescope, we'll be able to see much deeper inside these clouds and to see the stars themselves being born in those clouds. Just an example of one of many good places to look. Here's an animation showing the change of the view of the Carina Nebula as we change the wavelength. There's the infrared view. Now we're going back to the optical view. So we will be making very beautiful pictures, and you will see them change as we go to the longer infrared wavelengths. We will even be looking in the solar system. We have two major targets of future NASA missions, Europa, a satellite of Jupiter, and Titan, a satellite of Saturn. Both have been mapped by visiting payloads, probes, and they're very interesting for the study of possibility of life. So we know that Europa has an ocean covered with ice sheets, and that water is coming out and vaporizing into space. Our next mission will visit this small satellite and try to fly through the gas clouds that are coming up through the vents. We also have a mission to Titan, which is going to include a small helicopter to fly around on the surface of Titan. So we'll be able to monitor the weather on Titan, which has clouds and rain and lakes and rivers, and very similar geologically to the surface of the Earth, except, of course, the rain and the lakes are made of hydrocarbons instead of water. We have good reason to think that the surface, which we see, is ordinary water ice, and that there's a possibility of a liquid ocean underneath that surface. So it's a very exciting place to go looking. If there is any place in the universe where life operates on different principles instead of the ones that we have here, say using hydrocarbon solvents instead of water, this would certainly be a place to look for that possibility. We will be looking for exoplanets. This illustration shows what happens when a planet goes in front of its host star, as was seen with, for instance, the TRAPPIST system. The various little planets go and block some of the starlight. What's critical for us is that not only do they block some of the starlight, but some of the light of the star will go through the atmosphere of the planet on its way to our spectrometer. So that means that we can learn about the chemical composition of those atmospheres of small planets around other stars. So we already have a plan that includes 9 Earth-sized planets, 5 Neptune-sized planets, and 16 Jupiter-sized planets going around their stars. And we know where they are, we know when to look. And so this will be, I think, a very exciting upcoming proposal, observation. What I don't have on the chart is, of course, that one of our observations should be an observation of Alpha Centauri. People will look with our coronagraphs to see if there's a visible planet near there. There will be an early release science program. So this is the immediately released data that that I mentioned to you that are chosen from proposals. Many people participated in that. Their job includes not only planning the observations, but processing the data so that they're useful for everyone. So you can find webinars about all of these if you want to see them. There's some examples of some of these programs. We're showing you here that we will be looking for highly lensed galaxies. Jane Rigby at Goddard is the principal investigator for this one. They give us the chance, to see much more detail than we ever could see with an ordinary telescope. We're using the lenses of the universe to help us. We're looking at particular objects in known fields, and so many observations will be surprises, I think, from this. Of course, we don't just want to look, we want to see something that we did not expect. We'll be looking at the active galactic nuclei nearby, luminous infrared galaxies, quasar hosts, and even the resolved stellar populations in some very nearby galaxies. The Webb telescope can see better because it's bigger than the Hubble can do. We'll be looking at astrochemistry. So we'll be looking for Wolf-Rayet stars producing dust. We'll be looking at the photodissociation regions in Orion, and we'll be looking at the chemistry of ices in the star formation. So we have a very powerful instrument suite that's capable of measuring the entire spectrum from visible to mid-infrared. And it could all be interesting. We'll be looking even in the solar system. Here we have a picture of the Jovian system. Imke de Peter will be observing that. We'll be looking at many transiting exoplanets. And of course, exoplanet coronagraphs. So here's an example of one of the programs. We'll be looking at 15 targets to look at their atmospheres. So this gives a list of the particular planets people want to observe, how they range in mass and size. And I think we will find something very surprising from this. So to give you a little bit of a story about how we get the Webb telescope ready for launch, here is the trip that the observatory makes. Here in the top left, I show you the picture of the telescope itself as it was assembled in our clean room at Goddard Space Flight Center. After we put it together, we transported it to a vibration table, a shaking device, which was able to apply 50,000 pounds of vibrating force to this telescope to see that it could survive launch. When we were done with that and we confirmed that it would survive launch, we put it in a shipping container and sent it around to the Air Force base nearby, and the entire truck and shipping container went inside the airplane. It then flew. This is one of our largest military aircraft. The aircraft flew down to our NASA facility in Houston, Texas. And this is the door of the vacuum tank in Houston. This is called Chamber A. It was the same vacuum chamber that was used by the Apollo astronauts as they prepared for their own mission to the moon so very long ago. So after we had verified that the telescope would work at the very low temperatures that it will have in flight, then we put it back in the airplane, sent it on to California, and that's where it is now. We have now completed all of our vibration tests and all of our functional tests on that observatory, and it is being prepared for shipment again. We are folding it back up, and we'll, again, in a few months, we'll be putting it into a boat, and it will go through the Panama Canal on its way to the launch site in Kourou in French Guiana, in the north coast of South America on the equator. So this is a tremendous accomplishment for all of us. It's been a long time coming, and now we will go to the what might seem dangerous. We will launch it. Assuming all goes well, which we expect, then we will, in a few weeks after launch, we will have it unfolded and it will begin to look like this in space. Where are we going? We are going to the Sun-Earth Lagrange point L2. This was discovered by Leonhard Euler in 1750. It's a place where the combined gravitational force of the sun and the earth are able to pull the observatory around the sun once a year. So it stays near this line. It is a good place to put the telescope because a single-sided sunshade, a single-sided umbrella, can protect the telescope from the heat of the sun, the earth, and the moon all at the same time. So it's about 1.5 million kilometers away, 0.01 astronomical units. So very close by in relative terms in the solar system. Here is our scary movie. This is the telescope unfolding in space after launch. This is all done by commands from the ground. First, we unfold the antennas and the solar cells. Then we unfold the protective cover. And this is an extremely complicated folding process, but it's the only way that we have to produce such a large telescope and get it into space. So this is all done by remote control, but we do have one thing that's easier for us than the Mars landers. We can go as slowly as we like. So after each step is completed, we can confirm that it was correctly executed, and then make sure that if it was, or if it was not, then we have another way to do every step. Because everything was designed with electronic redundancy. So there are two ways to actuate every motor. Every motor has two sets of windings. Every actuator has two sets of ways to set it off. So here it is, a large telescope in space. And this is a view that, of course, you could never see, because in space, the telescope will be in the dark. So there are many ways that you can follow along with our progress. We have various websites and Facebook and so forth, links that you can use. Now I want to talk about the next steps in ground-based astronomy. As you know, we are working on 3 gigantic telescopes that are much larger even than the Webb telescope. The biggest one is the European one in Chile. It will be 39 meters across. It's already well under construction. They have started building it. The 2 American ones are a little smaller, and they're started, but they're not nearly as far along as the European one. So 39 meters is about 6 times the aperture of the Webb telescope. And so clearly there are things that the ground-based telescope can do that the Webb telescope cannot. So one of the things that we do on the ground to make sure that we get the best possible performance is we have adaptive optics. So the various ways to do this, they all require something to focus on in the field of view. So if you have a light coming from the telescope and you know that a thing is supposed to look like a star, then you can adjust the telescope with an adaptive mirror to correct for the atmospheric delays and make a nice sharp image of the star. We have what's called laser beacons that are used for this. They actually operate by illuminating sodium atoms in the upper atmosphere, and those then become artificial stars that we can use. Curiously enough, this picture also shows you that if you go to the eye doctor, your ophthalmologist, he or she will also have some of this kind of equipment. They need to be able to see inside your eye to see better, and they have adaptive optics for that purpose. The person that developed this system was the same person who learned how to measure and calculate the shape of the Webb telescope mirrors as we were making them for flight. So now I want to talk briefly about a new idea that we're working on. It's not actually so very new. One way to get better performance for these telescopes is to have a star in space to focus on. So we can put a laser beacon in space to simulate a star and use that for adaptive optics. So here is our concept. In this one, we are shining the laser beacon down on the Keck Observatory, and we'll get much better performance than it can otherwise do at visible wavelengths. So that's a pretty spectacular thing to try. Now, the most ambitious thing that I've been thinking about is this one. It's if you could do the same thing and also have a star shade to cast a shadow of a star onto the observatory, then you would be able to see little planets very clearly orbiting around their host stars. So here is a simulation of an image that you could take with this equipment, it would take 1 minute to get a nice exposure showing the Earth, Venus, and Mars orbiting around a sun-like star at a distance of 5 parsecs. So this is pretty hard to build, but it might still be easier than the telescopes that people want to put up into space. So a pretty remarkable result is that you could also tell if those planets had oxygen and water, if they are like Earth. So here are synthetic spectra, simulated spectra, showing that if you could make those observations, you could see the absorption lines of oxygen and water in the spectra of an Earth way out there. Of course, Jupiter and Neptune are much bigger and brighter, so they'd be much easier to see. But who knows what they really are going to be like. It's a very powerful tool that we've been trying to develop. So I think it's a time to conclude, and be happy to have questions from you about what are we going to do. Thank you. Thank you.
Thanks so much, Sean, for this outstanding masterpiece of work and outstanding conference. And so we have, and thanks for allow time to discussion. So, and questions. So we have time for questions from the audience. So those who would like to address questions or points, please raise the hand and activate the microphone. So our first question is from Nick Kaiser here in Paris. So please, Nick, address to Sean your points.
Very nice talk. Thank you very much. I was intrigued by the satellite guide star concept at the end. So am I right in thinking that you can use, if you only have one satellite, then you can only look at sources that are sort of very much in the same direction as the satellite?
Yes, that's correct. There's a number called the isoplanatic patch that tells you how large a field of view can achieve ideal imaging. It's a few arc seconds in radius depending on wavelength.
So
it's perfect for compact objects like active galactic nuclei. If you wanted to get the whole Hubble deep field, it would not be sufficient.
And then presumably the satellite's going to be moving across the sky, and so that limits the exposure time, right?
Yeah, yes, it does. But we found, of course, that there is a place where you can make the satellite stop in front of the background stars. We call it an astrostationary orbit. So it's a moment when the velocity of the satellite matches the velocity of the observatory. So we can actually achieve up to several hours of passive alignment within the isoplanatic patch. So it's
interesting.
It's this is not a new result either, but it's now what we've learned is how to place the guide star where we need it.
And so you'll be driving the satellite around. It's not just.
Oh yes, yes. It's controlling the orbit to the arc second precision that you need is not so easy, but we have mastered that now. We know how to do it.
Would an alternative be asking Elon Musk if he could put these instruments on his fleet of satellites?
Unfortunately, no. His satellites are all very low orbit, so they go zooming across the sky very quickly. They're a lot of trouble for our fellow astronomers because they interfere with the pictures. But anyway, on the other hand,
not a good friend.
It would be great if we could have 10 or 100 of our beacons, then you could always be looking where you want.
Yeah, very nice. Thank you.
Thank you, Nick. Hi.
So thank you, Nick.
Can I ask a question?
Somebody's muted there, I think.
Can I speak? Good afternoon. Good afternoon. Or are you in the United States?
Yes, I am. Yes.
Okay. So
Yes.
good morning or whatever. The story you told us is scary because is it? You said it's Lagrange L2 is 1.5 million kilometers from Earth. So
Yes.
no way, except robots could repair a malfunction. You explained about multiple actuation from the electronics, but because the history of the Hubble satellite had several failures and several visits to repair, so this project is basically a worldwide project. Everybody is crossing fingers to hope everything goes well in this fall. Would it be possible to send a robot to repair? How long is it taking to send the James Webb to his L2 Lagrange 2 position? And could we imagine if something fails that a robot could repair this telescope?
Good question. It's almost everyone's first question. This is kind of scary to be so far away, and astronauts cannot go there now. In principle, there are a few things that a robot could do. If the sunshade does not deploy correctly, then you could imagine sending something to help it. The instrument package is impossible to get apart. It was not designed for servicing. There are a few things you could imagine doing. For instance, refilling the fuel tanks. We do have fuel requirement to keep the observatory near the Lagrange point. And so eventually the lifetime will be limited by that. But that's probably good for 20 or 30 years. So, we had to design knowing that we could not fix it.
So the list of failures, of possible failures, is probably huge, but everything has been reviewed so many times. But are you saying that we could send some kind of a robot or a ship to have some maintenance done or repair, or if something goes wrong, or is it totally impossible?
It's logically possible. It's extremely difficult, and there's nothing that's very easy to imagine that you could fix. It was not designed for repair.
But everybody who's
say that future missions like the Nancy Grace Roman Space Telescope, that used to be called WFIRST, WFIRST, is designed with the possibility of repair. And we should have possibility of access by that time because we're building our new large rockets.
Because if you put on one hand the project that all the experiments that have been planned, and I suppose for several years, you mentioned a 5-year program. I mean, everybody around the world is expecting to get the share of time of his instrument. So that means the odds are, it's a terrible story. I mean, it's like the Russian, Russian, it's just, you mentioned your movie, the most difficult part is the deployment of the instrument when it be in the area of L2, and also to stay in this area is no problem, I suppose, because there are many satellites already in this place.
Yes, we do know how to do the navigation, and we have, although it might seem strange, we are already practicing. We have a digital twin. Yeah. We have a computer simulation of the observatory, and we are able to practice doing everything that we will need to do with the observatory.
Okay, well, thank you very much.
Yes, wish us luck. We have done everything that we should to do a good
We're
job.
going to
And now
pray.
still,
We're going to pray. We're going to pray. The non-believers are going to pray.
yes, thank you.
Thank you very much, and thank you for the question, for the discussion, and thanks, Sean, again. And so we have now next question. It was Jean-Pierre Martin. Please activate your microphone and address to Sean, please.
Okay, thank you. Good morning, Professor Mather. Thank you very much for this brilliant presentation. As you know, the launch of JWST has been delayed so many times. How confident are you with the launch date in October? And second question, where is exactly the Webb telescope now? In the States, en route to Kourou, or where?
Okay, well, right now we have only one or two more things to do. The telescope is in California near Los Angeles.
California, Northrop. Okay.
And we are now engaged in folding the telescope up to get it ready for shipment. So it's very careful, very slow, but we're planning to ship it to Kourou this summer.
This summer. Okay.
Yeah. And so
we'll cross the finger.
Yes, thank you. We do that. And we're also very diligent about planning all of the details.
If I may add something concerning an eventual repair, I understand that L2 it's difficult, but who knows, in a couple of years maybe we'll have the technology, NASA or SpaceX or what else. Let's hope there is no problem. Thank you very much.
Yes, thank you. Thank you. We are actually making it a little easier. We are making a pattern on the end of the observatory so that a robot knows how to recognize the pattern and how to grasp if necessary.
Okay, thank you.
Yeah.
So we have another question or point by Nick Kaiser. So please, Nick, activate your microphone and ask the question.
Yeah. Coming back to your guide star satellite, it reminded me a bit of a white paper, I think, that Chris Stubbs wrote some time ago, which was how to get sort of millimagnitude calibration for ground-based observatories. So for the non-experts, it's a kind of dirty secret in astronomy that the most fundamental thing, like how bright a star is extremely difficult to measure from the ground to better than 1%. Right? We talk about, precision cosmology, but doing 1% photometry is considered to be very good. I was wondering if you'd thought about providing that kind of facility. I think he wanted to have a tunable laser that would illuminate the telescope, and so you would get at any time you requested, you could get a perfect measurement of the transmission of the atmosphere.
Yes, in fact, we are working on that. We did propose to do that with this satellite that we're designing. And there are at least two different ways to get a calibration. One is the one you described with a laser or LED focused on the down towards the observatory. And the other one is much simpler. It's a small spherical reflector that reflects the sun. And we know the sun's brightness to better than 0.1%. If you know the reflectance of the mirror, then you have got a good calibrator there. So,
and all the telescopes around the world can see it as long as it's above the horizon.
That's right. We could support all of that. So it's as you say, it's a dirty little secret, but it's a top priority for cosmology, since we depend on the relative brightness of supernovae at different distances to establish whether or not there is dark energy.
I think that was Chris Stubbs's driving motivation, yeah.
Yes, so yes, our team members include people at UC Berkeley who are working on that.
The other thing would be microlensing, detecting very small microlensing events.
Yeah, there's a lot to do with very precise calibration.
Yeah, thank you.
Thank you, Nick. Thank you, Sean. And we have now Katia Grimani from Italy. So please, Katia, ask your question or address your points to Sean.
Thank you very much. Thank you Norma. Thank you very much for this beautiful talk, for this beautiful mission. And my question is about the possibility to detect circumpulsar and circummagnetars disks with JWST. Is a very important topic according to me, because these disks may, modify the environment of these compact objects, and there is not much about experimental data in the literature. So my point is, if there is any clue about the minimum and maximum masses of these disks that could be observed with JWST?
I think this is outside my area of expertise. I don't know enough about the objects. I can say that we have built a very excellent observatory, and is very flexible and very sensitive. But I don't know whether you need more sensitivity, or what wavelength you need, or whether you need better angular resolution.
No, in principle, it could make it. For what I saw about the, the performance, it should make it. But I'm not sure about the masses. So probably, if the masses are large enough, certainly it will be observing these disks, if they are there, of course. So there is not much in the literature. So it's just a very, very important topic, in my opinion. So I'm positive that this experiment will give important contributions in one sense or in another.
Well, I hope somebody wrote us a proposal.
Well, yeah, I do too many, I just do too many things, but this is something they really love. This is my, my heart is on this topic.
Okay, well, if nobody has already proposed it, then I recommend that you propose it for the next time.
Okay, thank you very much.
Yeah,
Yes.
we'll be happy to talk later.
Thanks.
Yes. Thank you, Katia. So please take the proposal seriously to write. So more questions, comments. If I just want to allow all participants. So if not, I would like to address about the science program shown on James Webb Telescope. How much you will go deeper than Hubble said in redshift? And for instance, I am thinking about these nice results Hubble and Frontier Fields have on find galaxies and deeper. So this will be, I mean, for theoreticians, will be very important to have and to see how much, please.
Yes, we thought about that, and if there is a supernova, we can see it at a redshift of about 30.
Oh.
There are not very many, so they're hard to find.
Yeah.
So that's about what we think is the earliest, most distant objects we can see, a redshift of about 30. There are probably not very many, because unless we have an interesting surprise, there was not very much activity yet at redshift of 30. Not very many objects were being formed.
Yeah.
So when I showed you the graph of the hydrogen and molecular hydrogen cooling, it basically said only the very largest, most unusual density peaks would be able to form galaxies or objects right away.
Yes.
So that's what we're expecting, is that although we have the capability of seeing them, that it's still very hard to find them.
And now, you know that, I mean, for instance, I am also asking this question for star formation, because depending of the nature of dark matter, and as you know, we are in particular in this school, and many people here, I mean, proposing and studied, I mean, you was there on this kilo electron volt dark matter, which have all the properties of the cold for large scale, and solve most of, I mean, the problem in the small scales, at the scale of galaxies, satellite, and so-called, I mean, many other problems. So if such a kind of dark matter particles exist, for instance, the more, I mean, stellar neutrinos at this scale, it could be, I mean, that's for very normal Feynman diagram mechanism, they decay, and it will be very early. And this decay just enhance the hydrogen production and form stars much more early than usually assumed. And that could explain too why, I mean, as far as the technology, I mean, of the astronomy were, and in particular space, were advanced, more deeper and deeper set objects which appear having activities were observed. So this will be also very important, I think, I mean, and for us, I mean, for many scientists, to have from from your results evidence that you go to this deep, at least 20, I mean, 20, and it will be very important.
Yes, my sort of great hope is that we will find something that we do not expect.
And that's
very good. The early universe at redshift of bigger than 10 is one of the places to look. I think it's quite possible that the universe has a surprise for us there.
And that's very good.
Example, I mean, I'm thinking, what if there was another class of objects that were able to form in the earliest times, and they're all gone? Usually we say, well, we should be able to find a current example of everything, something that's left over from early times. But if there were some objects that naturally could not live that long, then they're all gone, and we might still see them at high redshift. So that's my guess, something preceding the reionization, some category of new object. Yes. So there are plenty of mysteries about the luminosity history of the early universe, the clustering history of the early universe. And I think there will be a lot more to work on after we get some observations. So thank you. I think that's a great topic.
Yeah, it's great what you are saying, because it's not very usual to have this high perspective you are giving us about the energetic the very energetic early universe, to have a strategy of discoveries, and not just say constraining or have a space parameters, so real discoveries. So thank you, and perhaps if there are no other comments, just a very short one. I mean, connected, perhaps not a such high redshift, but about also the James Webb for supermassive black holes. I mean, the activity as energetic ones. And because, you know, we have the subject, at least theoretically, came to a maturity because of these different X-rays, radio, I mean, visible, I mean, for this energetic process. And I think that Shen Wei, because of all what you explained before, will complete and will be able to make these multi-wavelengths correlations and really go further to what we are seeing now. So it's necessary to be, I found, to be very well prepared. I mean, to have the groups ready to make the cross correlations. I mean, to have this big picture in mind.
Yes, well, wish us luck with the launch. I think it will go well, but everything is dangerous. So
Thank you. Thank you. So now I would like, I mean, this school, and we like also surprise and always to our best guest and lecture. So you know that, I mean, you have the Daniel Chalonge medal from now several years. And we have, the school have now from 2016, a medal which honored and paid tribute to Ecole-de-Vega, who you meet it, and from many times here in Paris and also in the United States. So I want to present, and these medals are always a surprise award. So even virtually, I want to thank you, Sean, for this occasion, this wonderful opportunity in this in this period of humanity we are now with this pandemic, to share with you all these exciting science views and to present you. I don't know if you if you see, I will put the Ecole-de-Vega medal. I don't know if you see.
you see it? Yes, I see it.
So Ecole-de-Vega medal, who was had coined it here in Paris. You know that Chalonge medal is from the French Mint, and Ecole-de-Vega medal is for the most traditional medalist in Paris. And from a beautiful portrait, one of the last portraits made by Katia Charlotte Blumenfeld, from Kathleen Blumenfeld and the Blumenfeld family in Princeton, Cambridge, and Paris, here in Paris, and doing art and physics too. And the medal in the reverse side said in French, Ecole-de-Vega, the gentleman of science, le gentilhomme de la science, theoretical physicist, Daniel Chalonge School grateful, Ecole Daniel Chalonge reconnaissant, and at the time was not named Chalonge-deVega School, is named from 2015, and in science with great intellectual endeavor and a human face. La science avec une très grande exigence intellectuelle et un visage humain. And as you know, shows all medalists of this school and the Chalonge-deVega School are ambassadors of the school. So we are very proud, and we want to thank you for this. So I hope we will have opportunity here in Paris to meet and to present to you physically the medal. But from now on, you are Ecole-de-Vega medalist too. Thank you. And I think in the audience, there are Anthony Lassenby and Nick Kaiser, who are also medalists of this school. Thank you, Sean.
My goodness, thank you so much. That's a very great honor. And I will be happy to have it in memory of Ecole-de-Vega.
Yes, yes. So, Sean, you are at home here, So we will continue the program along this year. You would like to present whatever news, share result, share all this wonderful program you are managing and you are doing, whatever with James Webb or with the other developments, adaptive optics. So you are most welcome. You have always a time here and a conference ready to welcome you. So whatever you will propose to share with us, you will have the opportunity. So thanks so much, Sean, and all my regards to Shane, and it's real important, this communication we have.
Well, thank you for the invitation. I'm delighted and surprised to receive a medal with Hector's face on it. So I look forward to seeing you in person as soon as it can be.
Yes.
And many thanks for the invitations. So
thank you,
best wishes
Sean.
to all of our listeners, and I welcome people to contact me directly if you have additional questions.
Thank you, Sean, and you are free to, to leave now. Always I leave open the room, the room for people who want to, we share or just to discuss among themselves, but please do feel free to leave us. We are very, very happy with your presentation and participation.
Well, thank you, Norma. Merci beaucoup.
And for people, there were people wanted, to know that yes, we will have, we are registering and all the presentations from the beginning and the discussion completely will be placed in the page of the program of this year of the school, together with the PDF file, which Sean will address, and we, as all the previous lectures. We have now also a channel, the Chalonge-deVega school channel, in which the YouTubes are available. And I just last but not least said that the program continues, and in 2 weeks we welcome next lecture in this program. Very pleased and also proud to have Nick Kaiser, who will in the 21 of April, who will present gravitational lensing in cosmology. So thanks so much and have a nice time, and santé and health. So bye-bye.
Okay.
Bye-bye.
Bye.
So, je vois que nous sommes Alba. Buonasera, buon pomeriggio. Alba, può attivare e riattivare il tuo microfono perché non ti ascolto.
Ah, ho capito. Eccomi qua. No, dicevo che anche questa volta è stato eccezionale, proprio una serie di aperture su outstanding lessons su, come dire, non so, the most future.
Yes, master, a masterpiece.
Sì, quindi.
Yes, a masterpiece. I mean, for astrophysics, really a masterpiece. And I should say because there were questions and so on. So I wanted to comment, and then after it was, I mean, you know, and so it was not possible. And so the presentation, the introduction, he delivered on the universe, things which are said. One thing, I mean, in all conference, the conceptual introduction he made, I mean, in just for everybody could understand that, but in conceptual physical introduction is really outstanding.
Outstanding.
No many people do that with the concepts on entropy, with the concepts of information, with the concept, a really deep introduction. And I'm saying that that Big Bang is not anymore a theory for the universe. This has been, there is no T equal to 0, and there is no Big Bang singularity, and so on. This is really very, very important. I mean, and he said just in 2 and 3 words. So it's really very, very interesting.
I think we have to make I don't know, a summary, a collection of these presentation. Yes, I know that they run in the school, but
no, Alba, but there is everything. All this is in the page. So it's in the all things with the PDF, and the videos are. And now we have also the channel. So the thing is just to give diffusion, and people go, and those who want to go deeper see the PDF and the YouTube or the video till the end or till the middle, and those who want just to get the introduction, go to the introduction and see. We cannot and the important thing is to do the diffusion, that people the people, other scientists or journalists or writers and do the diffusion of that, because do just this the summary of all that. It's just cross-correlate, for instance, what Ecole presented from exoplanet to what James Webb will do, because we don't know now James Webb will do for exoplanets, but there are. I wanted also to ask about exoplanets, but there were I allowed to speak other people and so on. So I think that yes, I heard you, Alba.
Yes, but
what do you think? What do you perhaps you have in mind other thing too?
No, but I think or write something about to summarize all together, because we are now in presence of all the most outstanding study future development. So make some summary of the point, the highlights. This for the food. for diffusion. In this 10 conference, all the point more important, more future perspective has been illustrated. So
yes, but you know that given the link, as I said, given the link and given the facts and just, I mean, the abstract in some sense.
Sì, ecco, the abstract, certo.
Then after, in particular, because the program is not closed, it just make partial synthesis of that. But what do you know? What do you want? You know that making a partial synthesis when the program is not finished, and also because I think this the way now these were done because before, because there was not the possibility of this registration, YouTube and all the video and together. As I said, the highlights are the program itself. I mean, given the title, given the links, you said otherwise it implies to make research work of course correlation to do something more that has been already presented. So and so we have a golden, much more said, a golden program here, and it's not the case to ask more. Is the case to make known this program and these outstanding lectures, because this is the point, that these lectures are outstanding and not just the usual program that everybody is doing in Zoom. And that is a point to do, how to diffuse and make a much more available this program in the said scientific journalist of whatever. I mean, you know what I mean. I think I am clear.
No, it's correct. Yeah, yes.
And so said is in any case is enormous. I mean, it's enormous success to have almost every week 50 participants. I mean, we are 50 participants, around 50 participants, sometimes more, sometimes around this, all in all the lectures, which is and people who follow, and you see how the discussion go on. I mean, the discussions are not trivial.
Absolutely, no, absolutely are at the top of the matter. Insomma, no, it's fantastic. Okay.
The discussions are not trivial at all, and we have people who made this questions from the audience who are not scientists. Some of them, or one or two of them, who made very important points in almost all the lectures, are not all scientists. Say scientists are scientists, but I mean not doing research or in with a position which is paid by to make research. Do you? So it's important. I think.
Absolutely. No.
I was very happy to see Katia.
Katya, yes. We had a conference this morning, so she was.
And why she was not in all the previous one? I mean, she should. So said to her to register, or I think she's registered. Yes. And where is her now? Is always in. Is near Turin.
Cosa? Who? Perugia?
Katia. Where is
in Urbino, is in Umbria.
Urbino?
Urbino, sì.
Sì.
It's working with Eliza, Pathfinder, and
Sì.
additional wave.
Sì, very nice to see her. I mean, very nice to see her again. I mean, do you remember
Absolutely.
she participated very well in the lectures and so on. Now, bonjour, Monsieur Sèvres, comment allez-vous? Monsieur Sèvres, vous m'entendez?
Je vous entends parfaitement.
Ça a été très, très bien, n'est-ce pas?
Oui.
Alors, moi maintenant, vous savez, je ne veux pas mettre muet à tous les participants quand je commence parce que le lecture va être muet aussi. Mais j'ai déjà, j'ai identifié, par exemple, un participant qui, parfois, il allume le microphone et l'interrompt parfois et ce n'est pas possible. Ce n'est pas possible. Il faut que les jeunes, si on participe d'une réunion Zoom, c'est qu'on ne peut pas laisser le microphone ouvert quand il y a la conférence. Ça, mais non, de toute façon, ça a été, tout a été entendu, hein, disons.
Ah oui, non, chaque fois c'est très bien, très clair, ça passe très bien, ça va.
Alors, nous avons une fois de plus constaté la loi de Gerard Toft, qu'il y a toujours une surprise avec Zoom. Et vous avez vu, bon, il n'y a pas eu avec nous beaucoup de surprises parce que tout a été, bon, vous avez vu. Mais cette fois-ci, elle est venue la surprise, bon, ça a été du Zoom, de la, oui, du
share
Zoom,
screen, le share screen. Ouais.
Le share screen, mais de lui, pas de moi, ni, non. C'était de lui qu'il a dû faire sans se rendre compte. Et ça, c'est sûr, hein, j'ai pu le constater d'autres fois parce que moi, j'ai une certaine expérience maintenant, aussi quand je participe à d'autres conférences. Et donc, il a dû, sans se rendre compte, vous savez, avec les digitales, ou les souris, ou les claviers, qu'il est passé dans la présentation des transparents, disons, des diapositives dans sa présentation, et ça coupait les chairs. C'était en fait, on voyait et c'était la figure qui avait du diagramme des câbles qui était une figure ancienne en quelque sorte, qu'il avait pris et qu'il avait mis dans un annexe, dans l'axe vertical et horizontal. On les voyait, les sexes, mais on ne voyait pas la figure. Et il y avait quelque chose là qui a bloqué moi je l'interprète comme cela, et en fait Et vous avez vu, je dis, il faut sortir. Et il l'a fait, mais ça bloquait, je le dis, de sortir et de les commencer dès le début. Et là, ça a dû... Donc, il a pu, bien sûr, il a pu, mais c'est toujours quelque chose. Si M. Toft était là, il aurait à nouveau constaté sa loi. Et il y avait, vous avez vu, qui était connecté aussi un participant de l'IAP qui voulait faire une question et qui après, il avait levé la main. Il y avait deux de l'IAP et après, il s'est déconnecté. Je ne sais pas pourquoi. Et même, il y avait un autre participant de l'Observatoire de Paris, qui n'était pas enregistré. Donc, quelqu'un a dû, oui, elle est connue, hein, vous le connaissez, Monsieur Sèvres, donc, c'est très bien, c'est très bien. Donc, comme je vais arrêter maintenant l'enregistrement, nous continuons à parler, hein. Mais j'arrête ici l'enregistrement. Et donc, j'ai dit pour l'auditoire, donc j'ai dit au revoir. Et nous nous verrons donc comme j'ai dit, dans 15 jours. Mais vous y restez parce que nous continuons, hein. Donc, je vais arrêter l'enregistrement.